Is the mic working? Okay, so thanks Sandro for a very nice introduction of the problem and describing the PLDA. So now I have an easy task. I will just quickly go through a RATS DARPA project, and more specifically it's a SRE task we are part of. And I will just describe the whole system, and I will just give you a very quick and fast overview. So this is a project sponsored by the DARPA, and we are there together with many other participants. And as you can see here, there is a lot of universities we are cooperating together, and there are actually the other teams we are competing with, like SRI and IBM. But now I will present the work of our team, which is called Patrol, and more specifically I will present the SRE part. I will quickly speak about what the RATS program is about, and then I will quickly describe the data set and what is the task description, and I will show you quickly what subsystem and front ends we used in our speaker ID system, and I will quickly show the architecture of our fusion and show you the results and do some discussion about the results. So the RATS project, it's sponsored by DARPA, so it's clearly aimed at the military data, and the RATS abbreviation stands for the Robust Automatic Transcription of Speech. And the data we are dealing here, it's really very noisy and distorted. So it's quite different from whatever we have seen so far in the classical task, where we already had some microphone clean data or telephone data, which are, if you compare them to this, they are completely understandable and clean, and this type of data, they bring a lots of new channel variability, and we will need to revisit every step of the core technology we've been developing for the years to be able to work on such data. The RATS program, it is not only speaker ID. There are several tasks. They are speech activity detection. That's quite important task, because really if you don't have a good speech activity detection, your speaker ID or language ID system will probably not work that nice. Then there is a keyword spotting, and as I told you, language and speaker ID identification. Data for this project, they are collected by the Linguistic Data Consortium, and the evaluation is done at SAIC. This is a Science Applications International Corporation, and I see it as a corporation maybe similar to NIST. I'm not so familiar with these US institutions. And our team, it's called Patrol, and it's led by the US company BBN. The nature of the RATS data it's based on all of the data are the radio communication data. So to give you some examples of such data is when you talk over the radio, and it's used usually in the law enforcement, military. It can be used in emergency and air traffic control and similar environments like that. So by the nature of the data, because it's a radio based, you will transmit over the air, it's very sensitive to lots of different kind of factors, and the quality is highly dependent on those. So the most important are the background radio interference, which can really screw up your data. Then even if the atmospheric conditions change, it introduces some other channel distortions, and also the bandwidth you have available for your transmitting is very important. If you have a narrow spectrum, it's much more difficult to transmit, and you're subject to more radio interference, and also the background additive noise is quite high usually, because the data are taken at some locations which are very noisy, or in the moving vehicle or on the battlefield. So it's very distorted data. Also, that kind of channel, if you speak to the radio, you probably wouldn't speak like you speak on the telephone with your grandmother. You hardly can hear the other person on the other hand. So you use the fast conversation turns, you use the excited speech, and it's completely different to the conversation we typically see in the telephone conversations. So of course we need some data to train on, and right now the data we are dealing with are the data LDC got by retransmitting existing telephone calls over some radio setups they established in Philadelphia. But of course, as I told you, this is gonna be quite different data than we are going to face in the real scenario, because of course the nature of the speech will be quite different. And the languages we are dealing with right now is the Levantine Arabic, Farsi, Pashto, Dari, and Urdu. So you can see this is probably because of this DARPA interest, and these all are in the Middle East. So they're probably targeting this area for right now. But of course, if you develop the technology which is able to work on such data, on such languages, probably it will be easily adapted to English and some other non-military tasks. So for the speaker ID, each speaker we got 10 recording sessions, and each session was retransmitted over 8 different radio setups. They differ in the equipment, in the bandwidth use, distance, and so on. And they are I would say they are very different. Maybe you cannot hear it by your ears easily, but they are quite different in sense of channel information. And the RATS project is interested in doing tests in different duration conditions. The easiest is 2 minutes enroll, 2 minutes test, but as you can see there is the whole range of different duration conditions till the 3-second enroll, 3-second test, which is, for now, it's almost impossible to do any reasonable results on that kind of condition. Yeah, we will see some recording.
For the speaker recognition task, because that's synthetic data set, right? You mentioned that one of the challenges was the intrinsic variability.
Yes, well, there are the real data in our evaluation set, but we are not able to show it right now, and we don't have a key for it. So right now, for what we get for training is a synthetic data, and probably the real data are quite expensive to get, or they are secret to show to us. They will actually run our system through some secret data we will never see. So they want us to iterate, and they don't want us to show the real data, and it's quite hard. We of course have to negotiate with them and try to convince them to collect the real stuff. The more real stuff we have, the better it will work for them in the end. But of course, in this project we also have to deliver the system. It's not only description like you have in NIST evals. It's really a project when you are supposed to deliver all of the technology, and they are supposed to train the systems by themselves. So probably they have the data they will try to work on, and they will retrain all of the subsystems themselves. So, but we have to have at least an idea what we are working with to develop the technology. So they are doing these retransmissions of the existing data. It's much cheaper than going into the field and do the real collection. So all of our speaker ID systems are based on the PLDA, as Sander was talking about in the previous talk. And we've got gender-independent systems here because they don't give us any gender labels. But anyway, it's more than 80% males, probably. This is why they are interested really in the military applications for right now, and if we run the gender ID system on the data they give us, it's 80% male. So it's more, you can more see it as a male system with some few females. I mean in the test set, not in the training set, because the training set is composed of some retransmitted standard databases for the speaker ID, this Mixer 4 database, It's quite old one, but it contains the languages of interest and a great variability. So the PLDA was trained on 160,000 files, but this number is quite high because we just took all of the data and we split them into 30-second cuts and added them to the PLDA to introduce some more variability and noise. And without those, it would be something like 20,000 files we have for training the classifier. And the development set we are testing on it's quite small actually. It contains only 68 speakers, and this is really bad. When we need to develop the fusion, we have to even split our development set into 2 independent sets. The results we are getting on this are probably quite questionable because 68 speakers, it's a small number. So these are various front ends we have used. I will probably not go to the detail. Of course, we have some baseline features which everybody uses all the time, MFCCs and PLPs. And we have them here as a baseline, and we are trying to explore several other different acoustic features which are supposed to be more robust for the noise. So these CFCC features which try to simulate the auditory system or functions in your cochlea, they showed up to work pretty nicely for this task. And then we've tried several other features. Lots of them developed actually here at JHU. These FDLPs and PLPs. It's the Hinex group stuff, so I think that people probably know it here. And we also tried cortical features. I believe they come from University of Maryland, right? And the prosodic stuff from Brno. But this prosodic system, it has quite some serious problem on the rats data sets. But to really even detect the pitch and such data, it's quite some difficult task. So this is a speech activity detection slide, but I will not go into the detail of what kind of various VAD we have here, but I will just try to play you some samples so that you can have an idea what the data are about. So these are data from three different channels. And imagine we have to do speaker ID on this thing, and even keyword spotting on that thing, and language ID. So the problem is that you can almost hardly hear the speech there. And another channel, I think it's the same. So it's quite distorted. And the last example, there will be some frequency shifts, I think. So these are the data we are dealing with. It's something completely different than we have seen in our speaker ID, language ID before, and in an ASR. And you can hardly understand it if you're listening to it like that. And the systems which are developed in this project should do the keyword spotting on top of this thing. Okay, so as I told you, it's quite sensitive to the channel because a slightly change in the setup or in the atmospheric conditions or whatever will introduce a new type of variability. So we try to see what would happen if we remove one channel. In this slide we've removed channel B from the training of the PLDA and see what would happen. And we can see that we get quite some degradation even if we remove 1/8 of the data. And this is probably because of the noise which is specific to the channel B is nowhere seen to be in the other channels. So we need to develop the more noise robust features for this, and this is the main issue here, and we will need to explore that more. Okay, this is an architecture of our primary system. This is a fusion, of course, and we try to put there as much variability as possible to be able to be prepared for anything. So actually, we used the 3 different voice activity detections and 3 different front ends, which were resulting in 4 systems, because this MFCC front end was based on once we run it with one VAD and then the second one. It all was producing I vectors, which went to the PLDA, and after the PLDA we calibrated the scores, and then we split our developments into 2 halves, and using jackknifing we were training the fusion. Fusion is just a linear combination of scores plus some bias to give you a nice combined log-likelihood ratios. The unsupervised VAD, well, it's a VAD that Najim and Zengua developed at MIT. It's basically a 2-pass VAD. It's energy-based. First you try to detect some high-energy frames, and in the second pass you run the pitch detector on these high-energy frames and even filter out the rest of the high-energy frames to only those where you are able to find some F0. And those frames we take as the voiced frames. Yes, it's energy and pitch. This one is neural network based, and this one is a simple GMM over speech and non-speech class. Okay, I will probably skip this slide. It's just an overview how the different front ends can do. As you can see, the CFCC's got the best here. They are a little behind the MFCC, which is always the baseline and usually the best one, but on this data set the CFCC worked the best. And the fusion results, you can see that we've got quite some nice improvement. We are going to 1.4 or 1.5 of miss at false alarm, or false alarm at miss 10%, and it's from 2.4 to 1.4. It's quite nice improvement. So the fusion is really necessary to do in this type of the data, and the fusion like that over several front ends. It's a standard technique everybody uses when they are doing the speaker ID system, not only for the data like this, but also for the clean data like the NIST SRE stuff.
What's the duration of the algorithm? 30 seconds?
Yes, this is the 30-second.
So those numbers are quite good, right?
Well, it's not so bad, but this is
Not real data.
no, this is our development set. So, but it's the rats. It's like I was playing. It sounds like that. But this is false alarm at miss 10% and miss at false alarm 4%. So these are not so challenging points as the new DCF or old DCF you see in the NIST SREs, but these are much easier operating points. Okay, so I will conclude this, and the basic conclusion is that when dealing with this kind of data, we have to really carefully revisit all of the steps we have in our state-of-the-art systems and adapt them to such kind of data. And we need to work more on the channel robustness and concentrate on the unseen channel. And yes, I wasn't speaking much about the side information in the fusion, but actually you can use some side information about the recording to even improve your fusion. The side information could be the language spoken or the duration or the actual channel of the recording. We were experimenting with that in the fusion, and it actually also helps. So I think that's all of the quick overview of the RETs. So any questions?
Since these are all synthetic,
Yes.
do you have the same utterances going through all the 8 channels?
Yes, we actually have them there.
So if you left out one channel
Yes.
from the remaining 7, could you figure out the variability due to the channel and somehow factor that in for the unknown channel?
Well, we have tried to remove it. That was the experiment I was showing, but so far...
No, but your PLDA, was it the full probabilistic version, or did you use the point estimate?
No, it was only the point estimates.
Because this is where it's more important. Right?
Yes, well, we are eager to try the new Sandro's approach to this and see if the I vector from that channel is gonna be uncertain, because we have not seen that. But of course, we will have to go back to the I vector extractor training to exclude the data even from there, not only from the PLDA. But yes, the I vector from the unseen channel, which we haven't seen anywhere, should be maybe less accurate, but the covariance is probably most dependent on the length of the utterance. So I'm not quite sure how it is going to work. We will give it a try. Okay, so thank you very much for coming.